If you find these videos helpful, please consider supporting AddOhms and the Bald Engineer on Patreon. Hey, my name is James and I'm the Bald Engineer. Welcome to an AddOhms live stream. This one's going to be fun. I've got a demonstration that I'm using for an upcoming video. I know it's been a while since I posted an AddOhms video, but I've got one coming and it's all about MOSFETs. And so in order to make sure that the video was correct, I had to do an experiment. And then as I was doing the experiment, I thought it would be really cool to share it with you guys. And I'm also trying something where I'm going to record locally everything I'm doing so that I can maybe use that footage in another video. If you've never been to an AddOhms live stream before, welcome. Just so you know, we are streaming on YouTube, Twitch, and Facebook. There's links and stuff and descriptions and things like that. And then after the stream is over, there is a Discord server that you can head over to, and over there we can keep the conversation going. All right, what are we going to do today? So let me start with a picture of my computer. Hide the chat. And what did I want to show? Actually, that's not what I want to show at all. All right, come over here. Oh no, where did my window go? Oh. Okay, so typically when we use a MOSFET, an N-channel MOSFET, it goes into the, it's a low side switch. And so that means it's connected to ground while our load is between the source and the switch because it's on the low side. What is not always clear to people is how does the voltage on the gate affect the voltage drop across the transistor? And so that's what I want to spend some time talking about. Now, what we're going to show is I've got my what am I trying to show? Sorry, I just forgot. Okay, so I've got a transistor set up. So check this out. Down here, I've connected an N-channel transistor, MOSFET. This is the FQP something. That's the really common logic level. And the way that I've got this set up is the MOSFET is connected to a load. And in this case, the load is this electronic load. And so an electronic load is basically like a programmable resistor. And so we'll be able to actually see, or I'll be able to actually set things manually on there to drive the load. Now, here's what we're going to do. I'm using the power supply to turn on the, provide the source voltage to the MOSFET as well as the gate voltage. And then we're going to change the gate voltage to watch how the voltage drop across the source changes. Well, actually, voltage across the drain, but whatever. And we'll watch that on the multimeter, which you can barely see. That's not good. I need to make an emergency transfer overhead. Yeah, there we go. Now we can see everything. What is the model number of your electronic load? It is a BK Precision 8540. I'm not intentionally hiding it. That's just the only place I could put the sticker. So, okay. I've actually used it in a number of videos, but I've never really talked much about it. Anyway. Okay, so I explained the circuit. Now let's just go make a measurement so we can see what's going on. So first thing I'm going to do is turn this guy on. I'm going to make sure that my load is in constant current. And then I'm going to need high current. And now we're going to set this to 1 amp. So constant current means that the load will adjust its resistance so that it is always it is always pushing, or it'll constantly change its resistance, so it's always drawing 1 amp of current. That's one of the cool things about using a load, is that you can set something like that. What I like about using this instead of, say, like a resistor box is this can handle up to 30 amps. And so it handles the heat quite well. The downside is the fan is stupid loud. Okay, now this one's going to be a little bit more difficult to see, and I didn't have a good way to do this, but it is what it is. So what I'm going to do is on the drain of the transistor, and so again, that's going to be this is the voltage that is showing up at this point. I'm applying 8 volts, and then we'll see how much current is actually drawn. I've set a limit of 5 amps, and you'll see why in a little bit. And then over here on my other channel, I can control the gate voltage, which right now is set to 3.3 volts. So in theory, when I turn this on, nothing happens. Oh, duh, I forgot to turn on the load. Okay, so the load tells us it is drawing 1 amp, and it shows us how much voltage is being dropped across it. Keep in mind that because the load is sitting between the voltage source and the transistor, its voltage meter is actually showing us its own voltage drop. That's why I have the multimeter set up. Oh, come on. Are you kidding me? What if I go this way? Nope, that's way worse. If I come... Okay, that's looking pretty good. I'm sorry, I'm looking at the screen at the moment. I'm doing the best I can to actually be able to see everything. That number is not anywhere near where I expect it to be, which makes me concerned. Something is not going how I expected it to. Okay, I don't know what that was about. BK Precision 8540, $1,200 on eBay? No. No, the 8540, yeah, if you look around on eBay, I got mine for less than 300. I mean, it's not cheap, but it's not ridiculously expensive compared to the other loads that are out there. Okay, so backing up, what I was trying to show is the load is measuring the voltage across itself, and then the multimeter is showing us the voltage drop across the transistor. Now watch what happens to this voltage drop as I change the gate voltage to the MOSFET. I'm going to come over here, make this 4 volts. So it's at 3.3, and I'm going to go to 5 volts. So now it's dropped down to 28 millivolts. Okay, and then just to really make a point, I'm going to take this all the way up to 10 volts. And you can see that our VDS has dropped down to 23 millivolts. So that's actually a pretty good number. But let's talk a little bit about why that actually matters. Okay. As we increased the gate voltage, the voltage drop across this transistor went down. And if we just think about Ohm's law for a moment, there is resistance in this transistor, and as its resistance changes and its voltage drops changes, the amount of power it dissipates changes as well. So let's do a little bit of an experiment and figure out how much power should this thing actually be dropping. So if we go to the data sheet for this transistor, where did my mouse go? And we look at this special curve, I call it special. It is the on region or output characteristics of this particular MOSFET. And what this graph actually tells us is what is the RDS, or the resistance between the drain and source, when the transistor turns on. What you might notice is missing is that there is drain current, there is VDS, or drain source voltage. These graphs are VGS. There is no RDS anywhere on this graph, except it tells us what the resistance on should be. So for an example, we're going to use 5 volts. And so this is 1 volt down here, and then, 5 amps through the drain. So this is 1 amp down here, so that's 2, 3, 4, 5. So this line is going to be the 5 amp line. And this curve is the VGS when it's 3 volts. So what this is basically telling us, if we just to make it easy, I'm going to say it's this line. This is telling us that it should be dropping 200, 300, 400 millivolts. But at that same 5 amps, if we had a VGS of 5 volts, we should be dropping somewhere in the neighborhood of 165 millivolts. And so by increasing VGS, we reduce the drain, the voltage drop across the transistor itself. So what I've done is I've gone ahead and done a little bit of math for us. And I said, okay, if I have a drain current of 5 amps and the VDS, according to this graph, is 165 millivolts, then the resistance is going to be 33 milliohms. And then using Ohm's law, so like I squared R, it's dissipating 825 milliwatts. And then if you double the VGS to 10 volts, notice what happens to the power dissipation. It drops by like 20-25%. And it's because as we increase the gate voltage, the resistance between drain and source comes down. Make sense? I hope. Not trying to make the math too complicated, but, you know, got to have a little bit of math. Now, let's go back to the circuit, and what I'm going to do now is increase the current to 5 amps, and then let's just do this let's do this actual measurement so you can see how it works. So let me come back over here. And let's see. First thing we're going to do is on our load, we're going to increase to 5 amps. So I'm just going to dial in 2, 3, 4, 5. And then I'm going to change my gate voltage to 5 volts. Let's start a little bit low. And let's check out what's going on. Okay, first up, the multimeter is telling me that it is drawing, or it is dropping 150 millivolts across the transistor. Almost said resistor. So let's put in 1.156. Okay, and now I'm going to increase our gate voltage to 10. And here, it's now dropping 130, I don't know what to call it, 133? Max said he'll have to duplicate the experiment for it to really sink in. I like that. Do we need a heat sink for 5 amps? Actually, that's part of why we're doing this measurement, is to show whether or not we will. Okay, so I've got my two voltage drops recorded. I'm going to switch this over to go to here. And so, like I said, so to calculate the resistance on, all I'm doing is taking the voltage divided by the current. It's just Ohm's law. And then for power dissipation, there's a couple ways you can calculate power dissipation. In this case, I'm just saying, okay, take the current squared, I squared, times the resistance to get 780 milliwatts. And so here's what we can see. At 5 volts at a VGS, like coming straight out of an Arduino, this transistor will have an on resistance of 31 milliohms and dissipate 780 milliwatts. If we double VGS, then we get a big drop in power dissipation. Now, since this is a TO220 package, this this is the traditional like larger transistor style package. It can handle it can handle something on the order of about 2.4 watts before you absolutely have to have a heatsink. So this is actually going to work out well, because this basically says with either of these at 5 amps, we don't need a heatsink. Okay. Now, it actually turns out this is working a little bit better when I set this up last night. So, okay. Now, long story short, what I wanted to point out with this and the experiment I wanted to set up was I have the transistor, and we're measuring how much power does the transistor dissipate, as well as, what's the actual on resistance. Oh, I should point out, these were our VDS and on, resistor on, which matches what the datasheet more or less says. So even though this datasheet doesn't say RDS on anywhere on it, I just realized you can't see anything. Sorry, guys. Let's do this. Yeah, sorry. Thanks, Max. Okay, let me re-explain what's going on, what I put in here. So just looking at this one, we had, what did I turn the VGS on to? What was the current for the drain set to? What did we measure for VDS? And then what did we calculate for RDS on and power dissipated? So to calculate RDS on, I just took the VDS voltage divided by the current, Ohm's law. And then for power, we just multiplied current squared, so 5 times 5 times this resistance, and that's our power dissipated. So what we ended up getting is with a VGS at 5 volts, like you would get with an Arduino, the transistor is dissipating 780 milliwatts. If we increase the VGS to 10 volts, and I'll talk briefly about how you do that, if you increase the VGS to 10 volts, then the power dissipated would be 665 milliwatts. Okay, so this is a pretty good drop, like what is that, like 20%, 25% drop in power dissipated by doubling the VGS. Now in this case, because this is a TO220 package, neither of these currents or VGS values would require a heatsink. So that would be good to go. Now, what I was trying to point out earlier is these are practically the same values that we got when we looked at the data sheet. So the data sheet said it should have been at 5 volts VGS, it should have been 165 milliwatts, or 165 millivolts. We measured 156. So pretty close. But there is something that is bothering me, and I want to cover that next. So someone's asking so the constant load always draws a constant current. Would a real load make any difference? Not really. The difference that a real load would make is just that it would make the math a little bit more complicated, because RDS on would be changing as the actual load changes. And so if we were doing say a real like product evaluation or characterization, what we could use this load to do is basically say, okay, when our load is asleep, or when our device is asleep, how much current does it draw? And then when our device is active, or different stages of active, what does the current draw look like? And then you would make your measurements from there. So in practice, if it was a real load, there wouldn't be much difference in what we're doing, other than we would have to do a lot more math to figure out what the power dissipation was at individual current points. This is just a way to validate at certain points. Hope that makes sense. Okay, check this out. Let's come over here. So right now, my drain voltage is set to 8 volts. And the load, remember, is connected directly to the output of the supply, and then this side goes to the drain of the transistor. So the load itself, if this was like our motor or whatever we want to call it, it's dropping 7.15 volts. source 8, load 7.51, and then MOSFET. And then the MOSFET is dropping 153 millivolts. So we'll just type this in. And then the difference is equal to this minus these two. I don't think I did that right. No, I did. Why is it mad? Oh, really? Is this why? Because it's a colon? Whatever. And then the other thing I'm going to do is get my engineering notation so that we can see, because I'm not, that's not what I wanted. Grab this, go like this, home, grab this. What is going on? Paint icon. What is, okay, whatever. Here's what I'm trying to do. I want to go numbers, custom, engineering notation. Okay, that's all I wanted. So here's what I was trying to get to is we only have two things in our circuit. We have the load and the MOSFET, but there's 300 millivolts missing somewhere in my circuit. So where is this 330 millivolts at? Any ideas? Okay, can still see it. Okay. Johnny is absolutely correct. Cables and connectors. So the reason I wanted to point this out is because I think people will want to try to replicate this measurement, and you're going to run into a slight problem if you're not careful. So what we're going to do is I'm going to call this measure number 1, and then we're going to sort of repeat a few things. Let's see. No, actually, I'm going to leave that. So first thing we need to get is some better cables. And I'm going to replace these. And actually, before I change a bunch of connections, I'm going to turn everything off. Get these out of here. I'm going to plug this in. Okay. And for a little bit of strain relief, because I don't trust myself, I'm going to tape these. Okay, can you still see that? Yeah, it's pretty readable. Okay, so first thing I need to check is if I touch these together, I get 0 volts. That's good. And now what I want to show you is the very first thing we're going to do is remeasure the VDS. And so I'm going to switch over to this. So now I've got my multimeter probes. And if you can't tell because of the light, these are actually gold tip. I really like gold tip probes. So I'm going to touch to the drain. No, this is the source. And then the tab is actually the drain, and that way I don't accidentally short something out. And if we look now, we're measuring across here. That's not right. Oh, nothing's turned on. Okay. So touch the source and then the drain, and we get 133 millivolts. And is that what we got last time? Let's go back to laptop. So last time, yeah, we did get 133 millivolts, so that's right. Now where I'm going to measure is, let's measure the drop from the load to the transistor. So I'm going to put, so you can see what I'm doing. I'm going to take and put one of my probes here. And so this is on this wire, which is then connected to this wire up here. And so I'm going to put a probe here and a probe here. Oh, that's way higher than it should be. No, that's actually about right. So this wire itself is dropping 400 millivolts. I think I missed something. Okay, I know what's going on. It got biased. Let's try this again. Up here to up here. You're still thinking 400 millivolts, huh? I don't know that I believe that. Oh, gosh. Nobody caught that I made a massive mistake. So I said the load was dropping 7.51 volts. It's dropping 7.145. So we actually have a difference of 702 millivolts. So let's do this. So from load to FET, we just measured 472 millivolts. Nope. God, the shortcut for this is not working. It's a lot I don't know, I assume most of you know this trick in Excel, but this pound 0.e plus 0 is engineering notation. And it's just easier for me when I look at this, as I can say, okay, yeah, definitely have 472 millivolts going on. And then I think I can increase that resolution. 2 is probably fine. So, okay, so the load to the FET. Now let's measure from, this should be a good one. We'll measure from the power supply to the load. There's another 52 millivolts. Okay. And then let's measure from, let's see, power supply to load, load to the FET. What else do I got? I don't need to worry about here's a good one. So now what I'm going to measure is from ground. Oops. Now we're going to measure from ground to ground, or basically the source pin of the FET. So I'm just going to poke onto there. And that gives us a voltage of 114. Wow. So what does all of that add up to? 638 millivolts. I'm going to turn this off for a moment. So, yeah, I'll good point, Stephen. I'll mention something about that in just a second. So check that out. The MOSFET itself is dropping 153 millivolts, but the cables in my setup account for 700 millivolts of loss. And then I would say the difference between these two are going to be measurement error, and there's probably another cable in there that I forgot about. But I just wanted to point this out. If you're trying to measure hundreds of millivolts at high currents like this, the ohmic losses or the ohm losses or the resistance of the wires that you're using make a difference. I mean, this is almost 1 volt of loss in a relatively low voltage measurement. So just to review, what we did is we measured a MOSFET with a load attached to it, in this case an electronic load, and then I changed the gate voltage, which changes the gate to source voltage of the MOSFET, which is how you control it. As I changed that, the resistance of the MOSFET changed, which means that its voltage drop changed along with the current going through it. Now earlier somebody did say, well, what if it was a real load and the load was changing? Well, then you're going to get a case where the voltage and the resistance of this thing is bouncing all over the place, but you can still sort of simulate what a real system would look like by simulating the worst case low, worst case high, and then average load current to get an idea of what's going to be dissipated on the transistor. There's more complicated methods, but it's there. And then the other thing I wanted to point out is when you're trying to figure out what the RDS on for a MOSFET will be, you need to look at this on region characteristics graph, or it's sometimes called output characteristics. And what you're looking for here is what VGS are you using, that's the different curves, and then you look for how much current you expect to go through the drain, and then that will tell you what the voltage drop of VDS will be. Once you know the drain current, which you should know, with the drain current, once you know what the voltage drop across the transistor will be, then you can just use Ohm's law to calculate what its RDS on will be, as well as the power dissipated. Now, the reality is I don't actually normally care what RDS on it is, because all I care is how hot is the MOSFET going to get. And once this gets over 1 watt, that's when I start to worry about whether or not I need a heat sink. Below 1 watt in a TO220, that's usually okay. And as Stephen points out, you should always be careful and not. You should always be careful when attaching a heatsink to a MOSFET or to a TO220 package, because you need to isolate the heatsink electrically from the MOSFET. Just a second. Do you have an opinion on high side versus low side switching? I don't have an opinion, but I can talk about it. What I'm looking for, I actually had a bunch of heat sinks. And I have no idea where I put them. Interesting. Okay. I actually have some heat sinks that are designed for TO220s, but instead I'm just going to make a point with these. All right, let's go to webcam. So, for example, if I have a heatsink, I would not want to just attach that directly to the back of the transistor. Instead, you would want to use some type of isolation method, which in this case are like something like this pad, or there are thermal pads that actually are designed specifically for heat sinks, for TO220 heat sinks, stuff like that. The idea is, though, you should never just metal on metal attach a heat sink to a transistor. If you do, you're setting yourself up for a really bad time. Okay. Since Johnny asked about high side versus low side, let's go ahead and talk about something there really quick. What am I looking for? Is it back? This one. This is a really great website, by the way. I don't mind stealing from this guy all the time. What I'm looking for, I thought I had them side by side. I guess not. So in this case, we were talking about a low side. Oh, you can't see what I'm doing. Laptop overhead. So in this case, we were using this low side configuration, and it's called low side because the MOSFET is on the low side of the load. And so one of the downsides to this approach is when the transistor is off, this load is actually sitting at whatever the plus supply is. So if you're using a 12 volt supply on a motor, the motor is effectively energized, or its potential is at 12 volts. And so if, say, a ground wire was to come in contact with it, it could potentially then turn on because there's now a path to ground. And so that's sort of a safety issue. So you have to be careful about what kinds of loads you put into a low side configuration. Now, low side works really well with NPN and N-Channel MOSFETs because the emitter or the source is tied to ground, and so the voltage drop from the base or the gate is basically whatever voltage you apply to it minus 0. Now, if we go and look at a high side configuration, here we go. The transistor is now connected directly to the plus voltage, while the load is connected between the transistor and ground. This is really nice because now your load, which is probably more likely to be exposed to a user or an end user, is no longer sitting active. The downside to this is the main downside to this is how do you turn this transistor on? So what you'll notice is there's a PNP for a BJT and a P-channel MOSFET or a P-channel for the MOSFET. You might also notice that the transistors are upside down. And so what has to happen is the gate voltage, in order to turn off the transistor, has to be as high as the voltage on the source. And so let's say you have a 12 volt source here, or 12 volts on the source here. To turn off this transistor, you have to apply 12 volts to the gate. In order to turn it on, you apply 0 volts so that you get a minus 12 volt drop, which turns on the transistor. Now that sounds complicated, but it's really not that big of a deal. You can't use an Arduino or a Raspberry Pi to actually turn these off. They'll always be on. What you have to add instead is a driver circuit. And so you have to actually use a transistor to turn on the P channel where the gate is getting connected to the positive voltage supply. And so this is actually not that complicated to set up. And in fact, part of why I was doing this demonstration is this is a really good way to get a higher VGS on a MOSFET so that you get even more of, or an even lower on resistance. Because if you use the high voltage supply to turn on the gate, then you get a bigger gate to source drop. And so all this takes is you add another transistor, and I usually use an NPN, just like a 2N222 or a 3904. You basically just use that. You connect a pull-up resistor, and then you connect the gate. So when this transistor turns off, that's going to put 12 volts drop across the resistor. That'll be 0 volts. No, when this, that's okay. I think that's actually hold on. Now I don't remember what I'm looking at. This is an N channel, and this is a P channel. So the problem is, I think some people get concerned because, so if this turns off, so that's 0 volts. This turns off and becomes an open. So now we have 12 volts here. If you turn this on, this shorts out, this becomes 0 volts. So then we see 12 volts drop across the resistor, which means the gate turns on. Yeah, so if you're using an N channel with a driver, one downside is that this method inverts the logic. So a high here turns off the gate, and a low here turns it on. And then over on a P channel, I think it actually goes the opposite now, because if I turn this off, this is off, that's at 0 volts. So, I'm sorry, if this is off, that's an open. So this is going to sit at 12 volts. And 12 volt. Yeah, so if this is 0, this is off. Yeah, so on a P channel driver, the logic is normal. Okay. that was actually a lot deeper than I was expecting to go, but I do think I'm going to do a video on how to do drivers. So right now I'm working on a video on voltage threshold, which is more or less the basis for the demo I just did. And then I want to do, after that one, I'm going to do one on high side versus low side switches, which is a really good opportunity to talk about P-channel and PNP transistors. And then I think I'm going to do a separate one on drivers. It depends on how long the PNP turns out to be. Johnny, the driver is inverting, is that what you're trying to say? Yeah, what I was trying to say is on an N-channel, or I'm sorry, on a low side switch, a driver inverts the logic. On a high side switch, the driver does not invert. It's normal, not normal. There's a word for it, I can't remember, but the logic follows. I mean, from a programming perspective, it's not a big deal. You just deal with it in code, but just wanted to point that out. Okay, let me catch up on chat real quick. Is there another way to isolate heatsink electrically without putting anything in between the pad, i.e. isolating the heatsink from the board? Sorry, Josh, I don't have a good answer to that. If somebody in chat has something, we can talk about it, but I mean, the only thought that comes to mind, there's companies like Berquist, whose entire existence is to make electrically non-conductive but heat-conductive materials to attach heat sinks to transistors. And so my guess is, in general, to electrically isolate, you have to add an isolation path. George says, have you ever seen oscilloscope music? I don't think so. I have an idea what that means, but if you send me a link on Twitter or Discord to what you're talking about, then I can take a look at that. Can you explain what saturation means in a MOSFET? Yeah, totally can talk about that. In fact, let me think, where do I have... thank you for the follow, Crizo? Let's come to here. So I wrote an article, 7 MOSFET Myths. And one thing I wanted to point out, if you look at this, this is actually the same graph I've been using. I just didn't have it colorized in the example here. So this is from the FQP 30 NP60L, whatever, the logic level FQP. So this is the transfer characteristics or the output characteristics or the on region. So drain current, voltage, the drop across the transistor with that certain drain current, different VGS values. And so notice how there's like this sort of shape where the transistor has almost a linear look to it and then it plateaus. So in a MOSFET, saturation is when no matter how much drain current, what is it? Oh man, no, I just forgot what we call it. Okay. Yeah, so I said this is flat. It's really not flat. Actually, there's a slight slope to it. But when a MOSFET saturates, changes in drain current don't really change, or it doesn't take much change in the drain current to cause a big change in the voltage drop across it. And so this is actually, especially when operating as a switch, this isn't a very desirable region because this is basically going to create nonlinearities and distortion in whatever circuit you have. And so generally with a MOSFET, you don't want it to operate in the saturation region. You want it to operate in the linear region because this is where the RDS is going to be the lowest value and it's predictable. You could use feedback to try to control where the MOSFET sits, but it's very easy to predict what's going on with the MOSFET here. This is the opposite of a BJT. With BJTs, you want them to be saturated when you use them as a switch so that you can get the maximum current through them. And so that does create a little bit of a confusion for some people, because MOSFETs, you want to be in the linear region, but BJTs, you want to be in the saturation region. I don't know how that ended up that way, but that's how it ended up. Played with a Arduino type board with the same power source, turning the load with a large capacitor, resulting in VCC dropping so low that the brownout detector reset the processor. Yeah, there's some, you have to be careful when switching a load using the same power source. Oh, because there's a large capacitor. It sounds like you were getting, something doesn't sound right. That shouldn't have been an issue. But I need to see a schematic to know for sure what was going on there. So, okay. All right. That's actually most of what I wanted to show today. It's getting to be about lunchtime for me, and I'm hungry. So just to recap, what we did is the primary thing that we did today is we looked at what happens as you change VGS for a transistor, and how does that affect its on resistance. And as we can see, the more voltage you can put on the gate, the lower the RDS will be. The lower RDS, the less power that the transistor has to dissipate, and you get more voltage drop across your load. So in general, you want to try to make this as large as you can. The cool thing about this FQP, let me show you what this is up here. The cool thing about this transistor, it's relatively popular. It gets called a logic level MOSFET because it only needs 2.5 volts on its threshold, on its gate, to turn on. Ideally, you want to apply at least 5 volts to it so that you get a really good RDS. But even at 2 or 3 volts, it's not terrible. You can't get. I think I calculated 10 amps is way too high to run it without a heatsink. But even then, if you could get the gate up to 10 volts, you don't need a heatsink. Never mind. My point is, it's a logic level MOSFET, and so even if you can't drive the gate more than 3 to 5 volts, it's still pretty good. But it's always a good idea to take a look at this output characteristics graph to understand how much power is this transistor going to have to dissipate. Okay? All right, I'm going to wrap up. Ended up being a short stream, but like I said, I want to get back to working on the video for that's actually going to be using this stuff. I just wanted to try out the demo and record some footage of it so that I can hopefully use that in the video. I will stick around and chat for just a few more moments, and so if you want to ask questions, you can. Remember, we do have an AddOhms Discord, so if you want to keep the conversation going, you can get a redirect by going to addohms.com/discord. With that, my name is James. I'm the Bald Engineer. Thanks for stopping by. If you find these videos helpful, please consider supporting AddOhms and the Bald Engineer on Patreon.